All right, so let's introduce our topic of soils here for the semester. And when I talk about soil, most of you probably are thinking about compost piles and worm bins and organic matter and fungus, mushrooms. All of those things are super popular right now, and rightfully so because they are very cool. And they're somewhat on the edge of what we understand in terms of science and classification. And there's some very intricate developments with microbes and how they interact with plants in the soil in particular. But when we start, we're just going to focus on the very basics. And I think the basics are pretty cool too. And it all is part of a complete picture for how we describe and understand soil and its relationship to plants. So here, our first lecture is just going to be pretty simple and relatively short. I'm going to introduce a few key terms and kind of show you a wheel. We're going to spin around and around that wheel as we go. We're going to start on one particular part of the wheel. So this lecture here will be our introduction to soils. Really, it's an introduction to soil science as a discipline. This one course you're taking is modeled after every other university course as introductory soil science. And so you can take this course and you can transfer to a four-year institution, and you've got your soil science credit taken care of. So because we want to model the wider discipline, each week we're going to be focusing on some slightly different or perhaps out there tasks. At sometimes you'll think of yourself as a geologist. Other times you'll think of yourself as a GIS map maker. And still other times you'll be a horticulturist using soil to grow plants. So here we are, our introduction to soils, and you can see our cover image showing the root zone of plants, and it looks like we've got some grass along with some clover up there, and this is down right at that root zone where we've got all the action happening, lots of things taking place right beneath our feet. So what is soil? It can mean different things to different people and in different contexts. But in its most basic form, soil is the broken down crust of the earth. So on the land, it's basically made out of rock, and that rock can be sedimentary or volcanic in origin. And then over time, it breaks down and crumbles up into small pieces. And that's what we understand as the basis of soil. And a lot of people call it dirt. Some people say, don't call it dirt, call it soil, because dirt is lifeless and soil is full of life. I don't care what you call it. I use the term soil and I use the term dirt. I don't hate dirt. I don't hate soil. It's all good. But I recognize that soil is the more scientific term. Now this image here is looking like pure soil, and this is actually a cultivated field where they're likely going to grow some sort of grain like wheat. And you can see it's been broken up by a plow, and there's big chunks and little chunks. But for all we know, this could be Mars because there's no plants growing. There's not much happening. I guess there's a blue sky that tells us it's Earth, huh? So as the Earth's crust weathers, that's the term, the crust weathers, it breaks down into small particles. And weathering is that process. And so the weather, the rain, the snow, the heat, the wind is part of the process that breaks down rocks into smaller rocks. And they get so small that they become soil, which is a size in which plant roots can grow. That's the definition of what counts as soil and what doesn't. So it's the particles that are the result of weathering that form the basis of soil. It's the majority part of what it is broken down crust of the earth. Some people call this regolith. The geologists in the room will say the crust of the earth that's broken down is called regolith. Horticulturists, we just call it soil. So here we can see that weathering is the term to describe the process of breaking down rocks in contact with air, water, and living things can cause weathering as well. The image in the background is taken from Torrey Pines State Beach. If you ever hiked around Torrey Pines, you see cliffs made out of sandstone. And over time, when it rains, that rain causes some very interesting erosion patterns. And that erosion is weathering. That's the process of breaking down rock and turning it into fine particles. In this case, most of the sandstone probably goes down to the beach, but it's in the deposition of the weathering where plants can grow. So this is a process that happens all over the place. It happens at different rates for different climates and based on different topography or slope, you'll have different rates as well. If we look at San Diego County, we look at the rate of weathering, and we recognize that the rate of weathering is relatively slow compared to other climates, although it's not the most slow on Earth. And the reason it's slow is because we have less rain, a little bit more dry, and less rain means less washing away, less erosion, less streams and rivers and floods. We still obviously have some rain, and that contributes to our weathering. When you look at the process of weathering, it's taking the original rock and breaking it down. So the name of that original rock is called the parent material. And that can be made of various types of rocks. And based on those different types of rocks, you'll have some potential characteristics that are unique. So the type of rock in which the mineral components of the soil comes from is called the parent material. And so looking at the map here of San Diego County, you can see we've got several different types of parent material. And when you're right on the coast, we have the sedimentary rock, that yellow band. And this is going back to dinosaur times in which it originated. So the Cretaceous and the Triassic. As you head in our first foothills, actually our first mountains, and I'm looking and I can see Mission Trails Regional Park, and I can see Otay Mountain. Those are old volcanic peaks. And then as you head inland, we get into granitic rocks, granite. And that's the image you see on the right is granite-based soil. And the parent material are granite boulders. And then as you head even further, you get into pure granite up near Julian. But there's a unique thing called the Julian schist, which is its own different type of parent material. Now, you don't need to memorize those different names or anything, but just recognize there's different types of parent material. When you look on the right-hand side at the image, you can see those boulders, which are characteristic of East County in San Diego County, and recognize that you can even see how they have broken apart. Some of them have large cracks in them. You can see water stains, and oftentimes it's temperature swings that cause the boulders to initially break apart. In particular, freezing temperatures really have a big impact on the rate of weathering. So when weathering occurs, let's say it's at night and it drops below freezing, but there was a little bit of water on the rock, condensation. As water freezes, we know that water expands when it freezes. All it takes is one little pore, one little crevice or crack. You get the water in there and then freeze it down, and you have hydraulic pressure, which is very strong pressure. And very small cracks can lead to the entire boulder splitting apart due to this freeze-thaw cycle of water. Even in the little crevices where before a large crack takes place, that little bit of water will be a habitat for life, for moss and for lichen, which are kind of lichen are an organism that's kind of a mix between a fungus and an algae put together. It's its own thing. And you've seen them before. They're all the different colorful things that cover and grow on rocks. Those even break down the rock with different acids and enzymes that they release and that they cultivate with microorganisms in order to help literally decompose or digest the rock. So the parent material is the rock that it came from. The process is called weathering. It turns into the small pieces of the Earth's crust, small enough for plants' roots to grow, and that's the classification of soil. So how are these little pieces deposited over time? They tend to form horizontal layers. The horizontal layers have to do with the rate of deposition. So over time, things are deposited and it's done repeatedly. You get a buildup in horizontal layers. But also this horizontal layering happens because particles of different size will tend to organize themselves vertically. So the big pieces tend to go down, the little pieces tend to come up. I think that's the case. And so these horizontal layers, not surprisingly, we call them horizons, the horizon, kind of like when you're watching the sunset on the horizon. We classify these soil horizons into some very typical, often repeated patterns. Now, I list 4 here, but you can list 5 or 6. You can break each of these down into subcategories, and sometimes the lettering system is slightly different based on which source you're using and what context. But this is a generalization. At the top layer, we call that the O horizon. And O in this case stands for organic matter. And the O is the wood chips, the mulch, the roots of the plants, the dead plant material that builds up on the surface. And it's not even really soil as far as we're concerned. You will get things that look like decomposed plant material in the form of like a compost. It's dark, moist, kind of fluffy, but there's usually not very much sand, silt, or clay in the O horizon. And so while the O horizon is very important, it's crucial for plant growth. It's not necessarily part of our strict classification of soil. So a lot of times when we test our soil, we scrape the O horizon away because we want to know what we've got down underneath. The A layer is the actual layer of soil, the first layer of soil, or the one that's on top. Therefore, it's commonly referred to as topsoil. The topsoil is typically very broken down and very mixed with the organic matter from above. So it's usually quite dark in color and also very rich in nutrients. And surprise, surprise, it's where the vast majority of your plant's roots exist. So at least 40% of the roots of plants are up in the very top layer of soil. But oftentimes it's much more of a percentage of plants' roots exist only in that topsoil. When we do construction, the old practice was to scrape the topsoil away because it's not easy to compact and get down to the subsoil and then build the house, and then that's what you get. But now with new construction laws, we recognize that topsoil is not a waste product, it's a resource. And so when they build, they go down to the subsoil, build the foundation, then they have to bring the topsoil back. We want to hang on to our topsoil. We don't want to lose the topsoil. It takes a long time for soil to be formed, and depending on the climate, it can take different rates, but the average statistic is that about 1 inch of topsoil takes about 1,000 years to form naturally. So in a day's time, you can come and kick it with your shoe and you can get rid of 1 inch of topsoil, and you just got rid of 1,000 years of progress. So when we think about soil as a resource, there's a question, is it a renewable resource or a non-renewable resource? And the answer is it's kind of both. Humans can build topsoil, so we can speed up the process. We do not make it ourselves, so we can't necessarily make it go faster than it would in nature, but we can make it go as fast as possible. We can help nature build topsoil as fast as possible. If we don't, it can take up to 1,000 years to build 1 inch of topsoil. And in that regard, it would not be a renewable resource because it will not regenerate in one lifetime. And so what we've got, we need to protect. And not only do we need to protect it, we need to restore and rebuild what we've lost, because we have lost and continue to lose topsoil at a rapid rate. And it is a great concern for the health of humanity and the health of the planet. So getting down to that B layer that I referenced being called subsoil, that's usually where it's kind of blocky and compacted, and the roots of your plants will still go into the subsoil, but it's hard to dig and the structure is just not very easy to work with for you or for your plants. And that's over time, subsoil can become topsoil, but it takes many, many years, thousands of years. And then eventually you dig so deep that you get to the bottom of the soil. There's no more soil left. And what's below that is what we call bedrock. Sometimes this is called the R horizon. There's A, B, C, D, E horizons. There's all kinds of different subcategories here, but this is general. So in this case, we'll say C is the bedrock. That's when you hit rock bottom. There's no going deeper without dynamite. And in that case, you become a miner and not a soil scientist. So the bedrock is the parent material, typically, from which the soil above originated. Now, sometimes soil can be deposited from another place, but we're not talking about that right here. So you have the O horizon up on top, rocks, debris, leaves, twigs, roots, and composted material that we typically describe as humus. Then you get down into the first layer of soil called topsoil. That's minerals plus organic matter, perfect for plant roots. Below that is the subsoil, which is slowly becoming topsoil. Difficult to work with, blocky, and typically uh, very difficult for your roots to even penetrate very far, although it does have some anchoring effects. And then you get down deep enough that you hit bedrock, the parent material from which the soil derived. When we look at a healthy soil, this is the percentage breakdown that is typically referenced. So this is what we may consider the ideal soil. And does this exist? It's hard to even measure, to be honest, but it's more of a concept. The key idea is that healthy soil is composed of 4 primary ingredients. The main ingredient is the mineral particles, and that's everything we've been talking about so far. It's the broken down rocks, the sand, silt, and clay, minerals that make up what you would recognize as dirt or as soil. And although that's the main thing you can see, it's only about 45% of healthy soil, a little less than half. What you also need in that soil is space. So yes, you have rocks and minerals stacked together and organized in horizons, but you need to have gaps, places where there's air, where there's openings. Those openings are filled literally with air, so with gas, and in a healthy soil, that would be 25% of the total volume. What that means is half of those gaps are filled with air. The other half would be filled with water. And this air and water balance is always in flux. So after a rain, there's maybe a lot of water, not very much air. Eventually, the water flows down into the groundwater, and you're left with that perfect wrung out sponge consistency. That's your air water balance. If the soil dries out too much, the percentage of air would be increased from 25%. Now, if you have compaction, you stamp down all those gaps. Obviously, you're not going to have the air or the water. The water we know is crucial for plants to grow. It's also crucial for the life in the soil to survive. Many of our soil organisms are more technically aquatic organisms than they are terrestrial because they swim around in the water, which are smaller than a drop of water, even the water habitats inside the soil. We also know that without oxygen, in particular O2, so oxygen, not just regular air, but oxygen itself, the microorganisms cannot live because they are oftentimes, we have animals and we have bacteria and other kingdoms of living things that all need to breathe oxygen. So we need air, we need water for the plants, and we need it for the microbes. That last 5%, that is the organic component of soil. And you can break that 5% down, the organic matter, into several categories. The living things themselves are organic. They're life forms and they're filled with carbon. So as they're crawling around in the soil, that's part of the organic matter in the soil. Those living things obviously are going to do what living things do. They're going to eat, poop, and then they're going to die. They'll reproduce along the way. So that is also part of the organic matter. So when the organisms die, they decompose. And when they poop out whatever they're eating, they are contributing to a somewhat mysterious material that we call humus. We do not call it hummus. That's the food that you spread on your naan or on your sandwich or your chips or your carrots. Humus, though, is a material that is the byproduct of decomposers, which are a whole host of organisms whose role on the planet is to eat dead things and then poop it out. Humus is something we're learning more and more about all the time. It seems to be a little bit variable and a little bit hard to classify. And there's some scientists that think humus doesn't even exist. If you have more questions about it, I'll hope to be able to answer that. But as far as we know, humus is like compost, pure decomposed organic matter. We call that humus. That gets mixed into the soil, and that's an important piece, crucial. Without it, uh, plants could not grow. And the final part of organic matter in the soil are the roots themselves from plants. And plant roots are dying all the time. Just like plants are growing all the time, they are shedding roots all the time. If a big limb falls and now there's less photosynthesis, oftentimes there'll be a corresponding dieback in the soil where the plant no longer has enough sugar to feed all the roots. And it's these roots that are in direct communication, literally communication with the organisms. It's just not communication the way we would recognize it as human to human, but there is information and material and resources being exchanged in a very sophisticated way. So this is our ideal. This is what we're shooting for. 25% air, 25% water. That's the pore space. Those are the gaps. And then the physical solid material, most of it is minerals, dirt, sand, silt, and clay. And a small amount, up to 5%, is organic in origin, decomposed plant and animal material that forms the nutrients for the plants themselves, as well as the house for the microorganisms that feed the plants. So there we go. Do you have any questions? If you do, feel free to reach out in the Q&A discussion. And we will, this is just the intro again. As I said, we're going to add layers upon layers. The first few weeks are short weeks, and we're going to get you up to speed. This is just some terminology to help set the stage, and we will go from here, diving in each of these 4 components of soil. We're going to spin around the wheel, and we're going to focus very closely on each one. You'll have a much greater understanding when you're done with this course, and you'll be even aware of what you are unaware of. Right now, there's so much you don't know. My goal here for this class is to open those doors and show you what it's like and maybe pique your interest. And if you're very excited, you can keep on going through the door and go and help us to learn more about the frontiers of our knowledge in soil science. Thanks a lot.